Hello there. So in this video so far we have our circuit set up and we want to find out why it's actually working, why we're getting a flashing with a circuit that just uses capacitors and transistors and resistors. So it doesn't have like any smart logic in it, doesn't have like a timer, but we want to find out why it's doing this repeating pattern of flashing. So let's do a bit of a, I changed that value. Let's do a bit of a zoom in and see. Let's see if we can zoom in on one of our capacities. So when we use this software, we know that green represents, the more green it is, the higher the voltage. When it's grey, it's at a 0 volts. And whenever we get a red, we know we're dealing with some sort of negative voltage. But if we look at our power supply over here, let's see if I can slow down that simulation for us. So our power supply over here, it makes sense that we have green is our 12 volts and our grey is our 0 volts, so there's a 12 volt differential over here. Let's look at our capacitor. We can see over here this capacitor actually has a bit of a red tinge to it. So if I actually hover my mouse over this end of the capacitor, we can see in our bottom right hand corner that our voltage is 90 millivolts. But if we look at the other side of the capacitor, we have a negative voltage. Right now it was negative 90, but it's going back up to 0. As you see, the color's going more to grey. So we are somehow in this circuit having a negative voltage. So there's a lot of weird stuff happening here. We have our transistors, and we can see that in a standard circuit how these transistors are working. When there is current coming into the center part of the transistor, it's like it's turning on a switch. So how these transistors work is when there's current coming in, it's going to allow flow to go through this transistor at a very easy rate. So that one just turned on. So over here, as this current is going in, it's letting flow through. So the current is going to choose the easiest route, and the easiest route is going through the transistor, because even though LED lights themselves are very low in resistance, they still have more resistance than the transistor itself. So the current is choosing to flow through the transistor, so the lights are not being lit. If we look at this example over here, there is no current flowing into this transistor. It is like 0.1 PA, so pet, I forgot what unit that is, but it's a very negligible amount of current going in. So it's actually blocked. This is like an open switch. It's not allowing the current to flow through. So the current has to flow through the LED lights, and that's how the LED lights are lit in that scenario. Then we can also see, so we know that it's definitely, as these transistors, when there is power going into the transistor, those LED lights are turned off. So to explain this, I'm going to draw a new circuit or open up a new circuit that only has, is simplified, and it's just going to have two. So let me just go there, File. I think we're going to open from a file. Open File. So here I have a simpler circuit over here that is just two. So firstly, it's just a single LED light, because we don't need for the simple example, we don't need multiple LED lights, and it's just two of them so we can see the interaction. So what we have here is we have the same thing. We have a voltage. We have a 10 or 12 volt source. That's fine. It's going through. We have our 10K resistors. We have our 470s. This is very similar to our original circuit diagram. So what's happening at this point right now is we have these capacitors. So let's do a bit of revision on what a capacitor is. A capacitor is an electrical component that stores energy. It stores energy, and that could be thought of, it stores some sort of voltage difference. So for this capacitor over here, if we see on this side of the capacitor, it is 1.8 volts, and on this side of the capacitor, it is 0.6 volts. And so if we actually hover it over, we can see that the voltage difference across that capacitor is about 1.1. Can I pause this? The voltage difference across this capacitor, this one over here. So on this side of the capacitor, we see at the positive side it's about 1.8, and on the negative side of the capacitor it's about 0.6. So the difference across this capacitor is about 1.1 volts. Okay, so far that makes sense. And so what the capacitor is saying is the capacitor will change its voltage across it, but it can't do it instantly. It's almost like it's almost like it's slow to change, and it's that slowness of it changing is why we use capacitors in circuits. If you imagine you need to have a power supply for a computer, and you have voltage coming in, but it's not very consistent, and you want to level that voltage out, you will have your capacitor. It's almost like a shock absorber or a spring in like a mechanical system that will try to even out the voltage. So as you change voltage suddenly, the capacitor is going to ease you into seeing that change. So we know here it's at 1.7 volts, so that all makes sense. But now when we run the simulation, so we have this capacitor, and so this over here is at 0.68, and so that means if this is at 0.68, that means over here into this transistor, this over here is at 0.68, which means something just happened. Something just happened as soon as this transistor got to a particular, as soon as this side of the capacitor got to a particular voltage, something happened in this system because it just flicked over. So over here, I already have some scopes that I've put in. And so what I did, let me show you how I did those. Let me remove these. So what I wanted to do is, this capacitor over here is connected to this wire. So we see here there's a voltage. I just right clicked and I wanted to say view in scope. So now that is viewing this wire. We're getting the voltage of this wire over here. Okay. Then let's let's right click this over here and let's view that in scope. So that's saying we're seeing the voltage or the current flowing through the capacitor. Now let me just fast forward this because it's going to be slow to start off with. Okay. And let me just change the scale. So we want this to be a maximum scale. We want this to be maximum scale. We want this to be 5. And we want this to be not 2. There we go, 5. So, all right. So let's have a look at. We have over here, this over here, the voltage is going up, and then something drastically happens when, right, once we get to a point where it gets to about 0.7 volts, that's when the switchover happens in the system. We can see that 0.7 volts, which is, what is this, 37.2 seconds, which should line up with this 37.2 seconds, the current instantly starts flowing through this transistor. So we already said that this transistor acts as some sort of gate. So how it works is, this over here is the sensor. When the sensor hits a certain voltage, it's going to allow current or electrons to flow through the main terminal of it. And the switching point is at about 7.7 millivolts. So we can see over here, as the capacitor, as it gets to 0.7 millivolts over here, it's going to turn on this transistor to allow current to flow through it. So let's watch it again. Okay, so we're starting up. So right now we have this capacitor. We saw it was red, so it was negative. The voltage ends up climbing. We'll explain why the voltage climbs, but for now we just want to see as the voltage climbs up, it's going up, and then here we go. It just hit to 700, and as it hit to 700, we see here there's a bit of a yellow line. I'm going to switch the color to. There we go. We see that yellow line over there. That yellow line represents the current. And so we see as soon as we get to the point where we get to about 600 to 700 millivolts, then we get the massive the current flowing through the transistor. So we can see how this transistor is turning on based on the current. But why do we get to this? Why do we get to this big negative jump in our transistor? Well, let's find out why. So over here, we know that this part of the transistor, so when this transistor is turned on, it's basically saying there's a constant connection between this line all the way through because it's providing no resistance. So this side of the second capacitor is connected. We can think of it as being connected directly to the ground. Right, and so, okay, we know that this is the ground, so that means this over here has to be approximately 0, and I mean, it's very, very close to 0. But we know that the position of that capacitor before was 1.1 volts was the approximate voltage difference across the capacitor. So we know that the left side of the capacitor had to be 1.1 volts higher than the right side of the capacitor, and that's how we get this negative voltage over here. So let's go and see that again, and let's try to slow that down and see what's happening. So this capacitor, I'm going to right click this capacitor and we're going to edit this in, we're going to watch this into the scope as well. So, and let's change that to a maximum scale, please. So the capacitor, let's just speed that up. Okay. So we know once our capacitor is fully charged, if we look over here, we can hover it and there's 1.17 volts separating this capacitor. Yep, we got that. But then, so there's then all of a sudden now our voltage is starting to drop. So, okay, let's go back to the point and see what's happening. Okay, so over here we see our capacitor is 1.1 volts, okay, and it's only able to get 1.1 volts. Let's see what's happening to the transistor here. This transistor has, this transistor is currently turned off. If we look over here, this chart over here says it's got zero current flowing through it, so it's not allowing current to flow through the transistor. Most of the current is flowing through the LED light, so the LED light is turned on. So we know that when this transistor is turned off, it allows this capacitor to be charged, and it has its 1.1 volts. Okay, let's keep going. And then over here, this line is slowly getting up to, once it gets to point, let's go real slow now. Once this gets up to 600, right, now it's opened this, and as soon as it opens this, this goes down to approximately 0 because it's connected to the negative part of the 0 from the power supply. So this still over here has, if you look at this graph, it was at 1.1 volts and then slowly it's draining down. But remember, the capacitor is saying it always wants to have that same voltage difference. So usually we can think of it, like in this case over here, as this part is being 1.1 and this part being 0.6. So we can know that's a voltage difference of 1.1. But it works the same if the left side of the capacitor is at 0, then the right side of the capacitor has to be at minus 1.1. And so that's what's happening in this system, because we're just saying this is producing a 1.1 volt difference across this capacitor. As soon as we say, well, the original voltage here isn't actually 1.8 volts, it's actually, because we've connected it, it's actually at 0 volts, so this has to be at negative voltage. So if we follow the negative voltage line of this capacitor, we see it's plugged up to the other transistor. So that's the same thing that's happening over here. That's how we get to that negative voltage. So the right side of the capacitor gets to a negative voltage, which means it turns off this transistor, and so it allows the current. So we can see here the reaction is between these two transistors, because the transistor will turn on when it gets 0.7 volts to connect to it. It needs time for this capacitor to recharge up to change the voltage between both sides to allow it to have 0.7 volts to go into it. So we see here, if we follow this line, as the capacitor, so the capacitor at some point had the 1.1 volts, but it does know that there is a change. It wants to try to equalize. It wants to try to equalize its, sorry, go back to its original voltage point, because it wants to, it recognizes there is a change. It is slowly getting to that change. It doesn't do it instantly, and we use that phenomenon to our advantage. As we see here, the voltage difference is going down, and then what happens when it gets to the bottom? So as it gets to the bottom, oh, so we see here, we see a massive spike. So what happened here is we had our system, so this LED light acts as some sort of a resistance, because it has more resistance than the transistor. As soon as this transistor is turned off, which we know this one's turned off because it's got the negative function, we already know that. As soon as it's turned off, this capacitor is now not directly connected to the power supply. The capacitor is in between the resistor and the LED light. So there is not, this over here is not connected directly to 0. It is something in the middle. So it is a value that is higher than the 0 at this point. In fact, we know over here we have 12 volts. Most of the voltage drop is through this resistor over here. It says there 10.4 voltage drop through this resistor, and through this capacitor, sorry, through the LED light, there is a it has a voltage drop of 1.5 going through this resistor, so through this LED light. So this voltage over here is some point in the middle of that. So because now this has a positive voltage, a higher voltage, it instantly pulls up the voltage on this side of the resistor, which turns on the other transistor. So the interaction between these two lights is all done by the fact that the capacitor has a voltage change, and it will keep that voltage change regardless of what voltage is on this side, what voltage is on the positive side of the capacitor. It will always try, or at the instant point that we switch the voltage on the positive side of the capacitor, it is going to instantly change the voltage on the other side of the capacitor, and then it takes time for it to adjust. If you think of it like when you're asleep and you wake up in the morning, you're not instantly ready to do stuff in the morning. Your body needs time to adjust from sleeping to being awake. Or if you have a car, if you want to accelerate, it takes time for you to accelerate. The same thing, the same sort of thing is with the capacitor. So that's one. And secondly, we use that charging, the relative charging term for the capacitor is what's actually powering, what's determining for the transistor to open and close. So it's an easy way, or a very simple way, using just resistors, capacitors, and transistors to make one switch turn on and to make two lights turning on. Our triple circuit is just getting a third one in the line, so you can just get another LED and you can use the same technique of getting the capacitor. So the whole point is the capacitor is charging up as the capacitor is changing the voltage difference between the positive and negative end. It's just using that to activate a transistor. This is also called, what is it also called? It's also called a multi-vibrator. If over here we have an Astable vibrator, if you want to see more information of it online, I'm going to change this one to white. There you go. So over here we have an example of, like, if you want to see more research of it online, an Astable vibrator, so it switches between 2 points. If we run this, we see we have the same thing. We have the flow of current flowing through here. It switches from one to the other, and this is very similar to the circuit we had with our lights, except we add a third one on. We can use this for, this is used in a variety of simple circuits, because we can see here it makes a very simple, like a clock mechanism, or we already said a flashing mechanism, but you can switch from one to the other. So you can switch from Q1 to Q2, Q1, Q2, and so you can have, that can be generate a wave. If you plug it up to a speaker, you can make a positive and negative voltage, so you can get a sound. So it's a very simple way that was used in early electronics to get some sort of a cycle happening with power or LED lights or some other source. So that's with relation to your circuit, and I would like you to go into your circuit simulation software and see if you can obviously build our major circuit, but build a version of an Astable vibrator, and I want you to see what happens when you start playing around with the different capacitance values and different resistor values, because they will actually change. They're going to change the way the circuit reacts, but I want you to play around with the system by changing the resistors and capacitor values on the Astable circuit that I want you to make, and I want you to determine for yourself what they actually change. When you change a resistance, do both the lights change the time that they're on? Does one light change faster? I want you to find that out, and I want you to understand why us changing individual values of resistors can do that. Now, just to change a resistor value, we can either right click and we can go to edit and we can just change that value there, or if you actually hold the resistor and use the scroll wheel, you can change between all the basic resistor values. So you can do that yourself. All right, say thank you, and I will talk to you next time.